Hey guys, good evening. We'll be starting soon. So, this is a special interview session where we'll be covering backtracking based problems. So, let us wait for a couple of minutes so that some more people can join and then we'll be starting. Okay, so backtracking is basically a programming paradigm which is very synonymous with the concept of recursion, and we use it predominantly for many different applications when without recursion also the problem can be solved, but it becomes quite difficult. However, with the backtracking being the approach and with recursion being the tool of implementing the backtracking approach, we actually see that the problem becomes much easier. So there are many such problems, and if you think of all the recursion based problems like finding the sum of digits and so on, you can actually see that in some problems, recursion specifies one way of reading through there. Suppose you have to find the sum of a number 5, 6, 3, 4. The recursion based approach is read the first number and then add it with whatever you get the answer for this number divided by 10. 5, 6, 3. And then you say, okay, in order to find out the sum of digits for this number, you will fetch 3 and you will find the sum of digits for 5, 6, 56, and so on. This is a traditional recursion based problem which is covered everywhere. But one thing is, when you are saying that I want to find out for this particular number, the root is very fixed. 5634 tells you that you need to first consider 4. Then this tells you that you need to find out for 563. This will tell you that I need to find out for 3 plus 56, and this needs to tell you that I need to find out for 5 plus 6. So the root is very fixed. There is no turning away from this particular root. You simply have got to do something like this, that if your function is f of suppose n, within that basically something like this, you have to perform that. You have to return n divided by 10 plus f of n modulo 10, which will give you the last digit n modulo 10, plus you have to find out for the rest of the number, which is n divided by 10. This is standard recursion. We will have all the base cases and everything before this, but you can understand this is standard recursion. But there are other set of problems for which the path is not known. By what means we'll be getting a certain thing that is not known. Backtracking actually helps in solving those problems, and using recursion actually those problems can be made can be transitioned from complex implementations to very easy implementations. And that is what our focus is going to be in this 1 hour session, to look into certain problems and to see how easily we can implement them. Okay, cool. So let's get started. The first question that we'll deal with, again a very common question, is generate all subsets of a set, of a given set. So you can imagine that the set has distinct numbers. So this S, suppose this S has got, S is the set, and it has got distinct numbers like 1, 2, 4, 7. And if you have to generate all possible subsets, basically, how many subsets are there? There are basically 2 to the power 4 subsets, which is 16. Why did I write this? Because every element has the choice of being taken or not. So we can say there are 4 elements, so 2 to the power 4 is going to be the answer. How this is coming? Basically, whether the first element is going to be taken, it's 2 times, 2 ways. Either you choose or you don't choose. Similar for the second element, for the third element, and for the fourth element. For the third element 2, and for the fourth element again 2. So we know there are so many ways. But now when you have to create the subset, there is an interesting observation over here. The observation is that when we are creating a subset, suppose a particular subset 1, 2 and 7. For forming this, you can say we have to take the first element, then we have to take the second element, then we should not take the fourth element, and we should take rather the seventh element. Rather now think about a subset of 1, 4 only. In order to form 1, 4, you are saying that we will take the first number, then we will ignore the second number which we took into consideration over here. We'll ignore that number, so we will go to the next number, which is 4, we'll be taking it, and then we won't go. So let us look at this part. Let us look at these two things, what it means to us. When I choose 1 to 7, I say that you will be choosing 1, then you will be choosing 2, and then you'll be choosing 7. However, when we are choosing 1, 4, we are saying something like this, or maybe we can represent 1 to 7 in this manner. We'll be choosing 1, then we'll be choosing 2, then we won't be choosing 4, and then we'll be choosing 7. Now see, if you have to go 1, 4, if you have to choose 1, 4, you cannot choose from here, you cannot extend from here. You need to go back and you need to say that over here, when I had taken 2, I don't need 2 anymore. I will rather choose another path where I'll choose that 2 is not there. And I'll say come ahead from there and choose 4, and then I'll say don't choose 7. Don't choose 7. So this is a different path, and in this path what I'm doing is I had chosen, like I have this much common in both the paths. I say that come back to the common part, and from wherever you are changing, you are becoming different. Try to follow the different path. Okay? So let us see in terms of the recursion tree, or in terms of a tree-like structure, how it looks like. If you have to form all the subsets, then basically it looks something like this. First, we have an empty set. Then it turns out that we have two possibilities. One is we can take 2, another is we cannot take 2. We cannot take 2. So we said, okay, take 2, and another case you do not take 2. I think 1 was the smallest element, right? Okay, 1, 2, 4, 7. So we will say we can take 1 or we may not take 1. So let us say we take 1. Another is we do not take 1, which is empty set. Now we will say whether we can take 2 or not. This is the level we are going to decide that. So there are 2 states. On each state we'll apply this operation. And we will see, we will have 1, 2, if we take 2. If we do not take 2, we'll be having only 1. If we take 2 over here, we'll be having 2. And if we do not take 2, we'll be having nothing. Now if I take 4, or if I decide whether to take 4, I'll have 1, 2, 4 as one possibility, and 1, 2 as the other possibility. Similarly, we'll have 1, 4 as this possibility if we take 4. From here, if we do not take 4, we will have only 1 as the possibility. Similarly, we have got here 2, 4, and we will have 2. Over here, we will have only 4 if we introduce 4, and if we don't introduce 4, we have nothing. Consider for the time being, because after this we have another level, consider you have only these elements. 1, 2, 4. 1, 2, 4. So these are the subsets which will be forming, right? And how did we do this? At every point, we decided that whether to take the current number or not, we are deciding that. That is why we have reached 2 to the power 3 possibilities. Now, how to generate these possibilities? Or rather, how to do we really require to store this? Do we really require to form a tree-like structure? How did I do this? I said that initially we have only one state. When I choose whether to take 1 or not, I've got 2 states. When I choose whether to have 2 or not, I've got 4 states. Then I'm getting 4 steps. How to form these subsets? Do I always need to store these things? That first I'll store these 2 things, and then I'll say that okay, from here I'll be getting these 2, from here I'll be getting these 2. Then what is the storage? There are exponential possibilities. We can understand it is 2 to the power 3 over here. So if there are n numbers, we'll have 2 to the power n possibilities. Storing 2 to the power n possibilities is often a bit difficult. Why so? If we have to store 2 to the power, suppose 30, 2 to the power 30 possibilities, it comes out to around 10 to the power 9. 10 to the power 9 different possibilities. And each of these possibilities you can understand that consists of either one integer or multiple integers. And we know that if you have to store 10 to the power 9 integers, then only it can exceed the memory limit. It can exceed the memory limit, and especially if it becomes something like 2 to the power 40, it becomes absolutely impossible. Even 10 to the power 9 is only impossible. 10 to the power 9 integers you cannot store. So much of storage can't be borne by us. So there is another strategy, which is basically the principal strategy of backtracking, which we use, where we say that we'll be starting from the root, we'll be stretching along the left to the last node, and once we reach, we'll be traveling up and then coming to the other part. So you see, these were 2 different subsets. We traveled up in order to come to this. Now, what is the next subset? This one. How will we come to this? We have to travel upwards and we have to come over here. And then how should we come to this? We have to travel upwards. What does this traveling upward mean? This means when we are traveling one step upwards, we are changing our stand on 4. Our stand on 4 was something like that we will be taking it at the left. Now when we came one step up and then traveled one step down, we said we'll be changing this stand. Similarly, when we say that okay, we are at 1, 2, 4, or we are at 1, 2, suppose, over here, now we'll be going 2 steps back and then coming down 2 steps in order to form 1, 4. What are we saying? We are changing 2 stands. One is that we should not have 2, another is we should have 4. So from here to here, in order to transition, I am traveling back 2 steps where I am telling that I chose not to take 4. I want to change that decision, and I chose to take 2. I want to change that decision. When you say I want to revise myself, so you go back to the root where all the other numbers have been fixed, and from there you come down and you decide 1, 4. This is going to be the approach. This is the basic approach. And then from here you will say again that I want to go back to the root, and from here I need to travel and come over here. And from here I'll travel to this part, from here I'll be traveling to this part. Exactly this is what we do in backtracking. But the coding implementation is so simple that we don't feel it. But this is what we do basically. So you can see when we are forming basically 1 to 4, from here when we are going to 4, if you have to go to 4, or basically suppose from 1 to 2, 4, if you have to go from 1 to 2, 4, what exactly are we doing? We are saying that go to the state of root, that is dismissing everything, then gradually come down. Gradually when you come down, you decide you won't be taking 1. You won't be taking 1. This is the first decision you make. So first decision you say that you won't be taking 1. Then you say that I'll be taking 2. So you will be taking 2 over here and you get 2. Then you say that I'll be taking 4 over here. And you said okay, taking 4, I'll be traveling this step and you will be getting 2, 4. This is basically the way we transition across the states. But in terms of the coding implementation, we have to think in a different manner. Why we need to think? Because that is simpler. This tree traversal is not that easy a thing, right? Every time whether there is something in the right or left, we have to check all those things. It is not that simpler. So it makes sense to now think about how we should do it in terms of a coding implementation. We can do something like this. We can say that we are at a particular stage. Observe over here. We are suppose at this particular stage 1, where we have decided that we will be having the first value, and now we have to decide what will be there ahead of us. We will say there are 2 different ways. There are 2 different ways that we can choose. One way is that we'll be selecting 2. We'll be selecting 2 at this step. If we select 2, then basically this subtree belongs to us. This is the set of possibilities that belongs to us. Okay, so I am saying that at this stage when we have chosen 1, we have 2 possibilities. One is to choose 2, and then these are the possibilities if we choose to. If we don't choose to, then these are the possibilities. Okay, so this is basically what we'll be doing. At every step we'll be saying something like this, that up to here you have got some elements. Now there are 2 possibilities, whether you take an element which is E or you don't take an element which is not E. So there are 2 different possibilities. In both these possibilities, explore differently. What are the subsets, or what are the subsets you can reach? So first time you choose E, and then you focus on what are the later things you can decide. So don't visit the elements up to E when you come to this. And then you'll be saying that okay, now visit all possible subsets, and this is something that you will do at every step. This is very easy to be done programmatically, and programmatically this is one thing that we'll see, how to make our implementation very easy. Okay, so anyway, I think we can proceed to the coding. That would make it interesting. Yeah, if you have any doubts you can ask. And which programming language, by the way, you all will like? Which programming language do you want me to just a second. Which programming language would you prefer? Okay, C++. So let us start. We'll start with this find subsets. Touch find subsets dot cpp. We'll have, okay, I created a folder, backtracking. Yeah. So let's see, we can maybe copy my template, whatever I have, to find subsets. Yeah, I'll be deleting all these. I'll clear the template. So int main, and now what shall I be saying? I'll take as input this guy, which is number, and then I'll form a vector ll a, which I'll be taking as input. So for I equals 0, ll I equals 0, I less than I plus plus, and I'll say I'll be taking all the numbers ai. And now I'll form the subsets in somewhat this manner. ll I equals 0, I less than I plus plus, or we can say find the subsets. I'll call something like this, a function again with the same name. Let's see if that works. Find subsets. There will be a subset that I'll be maintaining as I go through. So I'll be maintaining some subset. This is the subset. Okay, and then I'll pass this and say that I am currently at the 0th step. I need to go up to the nth step, and this is my current subset. So when I pass this, this particular guy knows that from the 0th step I have to decide what to take and what not to take. So he will have something like this, current index. He will have the number, the final number, and he will have some vector like this, vector subset. We'll be taking it by reference using this. This ampersand tells that we'll pass it by reference, otherwise it will now entail a lot of time in order to copy only. We shouldn't allow that. So fine. Now when we come over here, if we see that current has approached n, we'll form the base case. What we'll be forming, we'll see that later on. But first we should form the base case, and I think we should maintain a list as well. So this will store the list of the subsets. Okay, I'm sorry, this will be a vector of vectors. Why? Because I'll store all the subsets in this. So I'll be passing this list over here, and I'll be mentioning here as well. Vector list. Makes sense up to here? Any doubts? Okay. Now what we'll be doing is, we'll decide whether the current element should be placed or not. So that's simple. Just, if I choose that the current element should be there, think only in these ways. Suppose the current element should be there. What should I do? If the current element must be there, I will simply add, I'll push back the current element, or I'll push back the, I think the vector, I should pass this A, and hence we have over here this particular list of the given elements. So we have A. I'll be pushing A of I, and I'll be saying that I have taken A of I. Now find all the subsets that you can create using me, and deciding on all the next numbers. So it will go something like this: find subsets car plus 1, that is, it should now choose from the next index. So I'm saying now see from car plus 1, go up to n and use this subset that I'm forming and add them to the list, and this is going to be again your principal component. This is when I'm deciding that okay, I must be adding this AI. Let us see what happens. I'll say that as you will reach the last point, where you'll reach the last index, you have nothing to do, you just have to add this subset. So if you have to add this subset, you need to do something like copy. So you can manually copy them, something like this, or maybe you can see how to copy as a vector in C++, either copy or clone, something like that will be there. C++ command to copy a vector. Do you know what is the command? Copy a vector. It should be a by assignment operator. It's a bit strange. Okay, so the reference is not passed, is it? Then we can try maybe. If the reference is not passed, we can say that okay, when I'm adding it, do something like list.pb. We'll check it whether this happens correctly or not. Now we will say I'm going to print them. So something like this: for or auto x inside list. So whatever is there inside list, I have to print each of them. So each of those I take inside x. Does it happen this way? List.pushback subset. Yeah. Okay. Yeah. So does it happen this way? Auto x in list. Maybe I can try something and see if it works. And del. This is just just checking whether it works. Okay, fine. So x in list, this does not take place, but okay, I think if we choose the recent one, use G++ with I think that's a very common thing, G++ std17, something like this. Okay, I think I need to check it. I don't remember these things. So compile C++ file using C++17 extension. Yeah, C++17. Minus std equals to C++17. So it's minus std equals to C++17, something like this. Yeah. Now we have A, and instead of A we will have cut. The rest of the things I think it's working perfectly. Cool. So now the only thing we have to do is we have to print the subset. So for auto y in x, we'll be printing that cout y with a space, and then we'll be printing an extra line after each. So keep in mind what we have done, and then we will see. dot slash a dot out. Suppose there are 5 numbers, 1, 3, 4, 6, 7. Segmentation fault. We are facing a segmentation fault. That's a bit strange. It won't give us any hint as well. In case of one number, we have 5. Then also there is a segmentation fault. AI, I think we are getting up to here correctly. Find subsets for this. I don't think the segmentation, it should be something over here. 0n subset list A. Card equals to n. We are not allowing this to. Okay. I'm not returning this. I should return from it. That's the error. I say if card is equal to n, then don't proceed, else proceed. 1, 3, 4, 6, 7. So I see that only one particular subset is formed. Why? The reason is that over here, according to this diagram, what it is doing is at every step it is deciding that I should add the number. If I always add the number, then something like this will happen. It will add 1, then it will add 1, 2, it will add 2, and then it will add 4, right? So, not pop back. The reason is that, basically the reason is that I'm always adding this. I'm not choosing what to do if I don't add this. Okay? So I can say that, okay, let me, I can either do pop back after this, or I can say before this, take another case that I won't be pushing this element. I will say without me, do add the element. Okay? Do add the element. Now let us try to understand what it will say is that without me first try, then with me do try. And why are we saying so? First of all, let's see whether this works. We'll see 5, 1, 3, 5, 6, 7 suppose. Now let us take a smaller value so that we can see the entire thing. 4, 1, 3, 4, 5. Yeah. I'll stretch it. You can see how it is forming. First time it is saying that we won't be taking anything. So it takes nothing. Then it says that I'll be taking only 5. So it took 5. Then it said that I'll be coming back one step and I'll choose to take 4. So it took 4, and then using 4, what are the two things possible? 5, 1 is... Okay, now it is interesting. You see, now it is interesting. You have 5, 4 and it is 5, 4, 5. What is the reason behind this? What is the reason behind this? The very reason is that in this particular subset you are deciding to push it. But when you are leaving the subset, you should also restore it. You should say that, okay, I considered for my own self to push it. But when I'm leaving this place, I should return it back to the condition in which my parent passed it to me. And hence, whenever we see this, it makes sense to do something like pop back over here. When we do something like pop back, why are we doing this? Because when we have added it, this is something that belongs to this particular iteration, but not to its parent function. When we'll be returning, when the control is returning to the parent function, suppose after it prints 5, it will return to 4, and then 4 will add itself. At this moment, only 4 should be there, not 5. Pay attention over here. What I'm saying is at the extreme left, now I'm arranging it like this. Now I'm arranging somewhat like this. First, I'll not keep anything. I'm not going to keep anything. I'm not going to keep anything. I'm not going to keep anything. And then I'm getting empty set over here. Then I said I'll be taking 5. Now, when I go back and I say, okay, I'll be taking 4, and then I'll be choosing whether to have 5 or not. I should not have 5 over here. So when I'm sending it back, I should remove this 5 so that when it takes 4, it has only 4. But in its state, what was I doing? I was retaining this 5. As a result of it, I was getting 5, 4 over here, and over here after I add 5 and I don't add 5, I'm getting these two things, 5, 4, 5 and 5, 4. So that is the thing you have to keep in mind, that when you are passing from the child to the parent, what is the thing that you are passing? Are you restoring it? So we can see that, okay, supposing that its children are going to restore everything. If we imagine that these are not going to change something, these two things are not going to change anything in terms of the state of the arrays, then we can say that I'm adding something and then I'm removing it. So I'll not be harassing my parent. Similarly, all of them will follow this particular path. They will say, before this I'm not changing anything. and they will say like this find subsets. But inductively, what can we say? That find subsets, the child is not going to change anything, this child is not going to change anything. I'm going to add something and then I'm going to remove that. So I can say that if all of the children follow this rule, every parent will get back exactly the same thing that they passed on. So let's check now. Okay, so there is an error in this pop back. Expected 0 found. Okay. So in pop back, basically we say that pop the last element. That is the reason. I think this should be fine now. And what is the guarantee that it will always be the last element? That is again something to understand. Again, if nothing is changing, then this element A car stays at the end, right? So suppose you have formed this, you have formed something like 4 or 3, 3, 4. So you had 3 which your parent gave you, then you added this 3, 4. Then you gave to your child. Your child added 3, 4, 5 and then it did a pop back. As a result of the pop back, what will happen? The 5 will disappear. So when it will come back, it is again 3, 4. So when you do pop back again, the last element 3 is going to disappear, 4 is going to disappear. So your parent again gets 3. When you are going to pass, this will again be 3. So this actually makes us understand how the recursion flow is working. We can check it over here. 4, 1, 3, 5, 6. Yeah. So we have now the perfect like the way we want it. First thing, we are first to represent that we are not choosing 5. We're not choosing 1, 3, 5. Then we said we'll be choosing 5. So we said 5 and 5, 6. Then we said we'll be choosing 3. Using 3 and using 5, 6, these are the 4 things I can form. 3, 6, 3, 5, 3, 5, 6. Then I said I'll be choosing 1. So using 1, these are the 8 things that are possible. 1, 1, 6, 1, 5, 1, 5, 6, 1, 3, 1, 3, 6, 1, 3, 5, 1, 3, 5, 6. Makes sense? Straightforward implementation. What will happen if I bring these 2 lines after this? Or suppose I change this order to something like this. I can say that this pushing should happen before and this popping should happen before as well, something like this. What will happen if I do this? Will it work? So in this case, what am I doing? Again, see, forget find subsets because we'll prove by induction. Suppose that find subsets do not change my state of the object subset. So what am I doing? I'm adding this value, I'm exploring everything while I've added this value, and then I'm popping everything. So again, I'm restoring the state of the object. So if everyone restores the state of the object, then the world will be a good place, right? If everybody is non-corrupt, right? But the order should be different. Do you understand that? If we do this, the order will be different. Have a look. You can see. Now the first time we have taken all the numbers. This is the line. We have taken all the numbers. The next time we have said that, okay, the last one we won't be taking. Okay, so just the order is going to change. The output is going to be the same thing. We just, prioritized the, the step when we are considering an element. And the other code looks somewhat like this. I'll be changing this now, or I'll be restoring this. Yeah, the other code, this is also fine. You can see what this did was it first said that I'll be passing it without adding it. Without adding that element, we'll be passing it, and then we'll be adding the element, and then we'll be passing it. Okay. Okay. Does this make sense? Any questions up to here? Cool. So we have seen subsets, and now we'll switch to some other question. I have 2-3 questions on the plate. Let us select one, probably this one. This is also numbers, and this is also going to be somewhat subsets, but this can be a multi-set. Okay, let's look at the question. This is called the combination sum problem. Quite important for your interviews, and yeah, mainly interviews. Backtracking only helps in very easy coding contests. When in coding contests you don't have much difficulty level, then backtracking can help. Another, application of backtracking is when we say that the number of unique states is less, then we apply DP over here. Okay, DP helps in reusing the states which are revisited. But anyway, backtracking, other than that, like in the easy coding contest, sometimes they just want to check whether the student can implement or not. So backtracking is very essential over there. If you want to like easily implement things, then this is very essential. Let us understand what is this problem. This problem says that you have to form a sum. Okay, you have to form a certain sum, and you have to show all the possibilities of reaching this sum using certain elements. These are all the candidates. These are all the candidates. Suppose the candidates are 2, 3, 5, 6. Okay. Now if you say, I want the sum of uh, 9, suppose. Okay. I want the sum of 9. Then what are possible? We can have something like this. We can have 3, 3, 3. We can have something like this, 2, 2, 2, 3, right? We can have something like 2, 2, or 2, 2, 4, and then 5, right? What else? We can have 3, 6, right? Anything else? These are possible in order to form the sum of 9. Anything else? So we have to consider one possible permutation. Okay, we cannot say that now 2, 3, 2, 2, 2 is another example. Only like one possible permutation. We'll check for each of them. Okay, cool. I hope there is nothing else. So we have to find out all the possibilities of uniting them so that we get 9 as a sum. How can we approach this problem? First of all, we know that forming 9 using some positive integers can take at most 9 steps. So there can be at most 9 steps. At most 9 steps. So if I say that okay, I've got 9 blocks, I can choose 9 or less than 9 steps, and I'll be using these 4 numbers. So basically I've got 4 to the power 9 possibilities, or maybe 5 to the power 9. 5 to the power 9, why? Because for every possibility I'm checking whether I should take any number, and if I do take, which of the numbers I should take. You can say that okay, no, I'll be only taking 4 to the power 9. Fine. Take it, at least 4 to the power 9 possibilities will be requiring, which is way too high. But the more problematic thing is after you get all these numbers, you will have something like this. You will have 2, 3, 2, and then on some other case you will have 2, 2, 3, and both are the same. For our problem, both are the same thing. We want only one particular out of them. So can we apply something easier? Because here if it crosses 10, then it is becoming way out of our feasibility limit, right? So our sum, basically it can be our n, the number of candidates can go up to 16, and the sum, it can be anything. Okay. We can say the sum is going to be less than equal to 200, whatever. Okay. Or basically you have a very small sum. You can have something like less than equal to 50. Try to find out how many ways you can reach the sum up to 50 using at most 16 numbers. But forget about the constraints. Think about how we can solve this very easily. Remember only one combination. How can we decide that? Think about it for a while, then we'll be discussing on it. So I'm taking another session today evening, that is on min stack. You can set your notifications. It's at 6:30. No, 6:30. This is ending. I think it is at 7. Main stack is a very good approach, and you can learn a lot of things in that particular problem. So if you are interested, you can come over and join. And before that, let us look at this problem. Can you think of something backtracking over here? Let us see in this way, that for every one of them, we know that only one permutation exists. Let us make it a point that we'll only proceed in this order. So after 2, or after 3, I won't be taking a 2. I will take some 2s, then I'll be taking some 3s, and then I'll never be taking 2 again. Okay? I'll be taking only 5. After 3s, I'll be taking only 5, and then I'll be taking only 6s. This can be of number 0. This can be of frequency 0. Frequency can be 0. I'm not really worried about the frequency. But after 5, I shouldn't be placing 3. If I fix this in mind, then okay, I can I can show one particular permutation of every possibility, right? If I fix this particular manner, so I'll be saying that while I'll be choosing whether to place 5 or not, I'll ensure that okay, whether I place 5 or I don't place 5, after this only 5 and 6 are going to come. I won't be having 2 and 3. And if the same thing I decide for every person, that okay, after me none of my predecessors can come, then we can ensure the arrangement, right? We can ensure that multiple arrangements of the same kind of thing doesn't come. Anyway, people have every liberty to understand what they require or what they should attend. So anyway, what can we use over here? At every step, suppose we maintain something. We maintain a particular list that we have chosen. Suppose we have chosen 2 and 2. Then what can we say? Suppose we have chosen 2 and 2. There are two possibilities we can see over here. When we have chosen 2 and 2, we know that the last guy is 2. So after this, we can choose either 2 or 3 or 5 or 6. Right? So what can we say? After this, let us try choosing 2. If we choose 2, we'll get something like this. 2, 2, 2. And then we can say after this, we will see there is only one possibility, which is 2, 2, 2, 3. Then we will say, okay, we are chosen to place 2 over here. Let us choose 3. And when we are choosing 3, we are having something like this, 2, 2, 3. We are mandating that now 2 cannot be used. We can use 3, but we cannot use 2. And we understand that, okay, this is not at all possible. We are reaching 4 plus 3, 7. And you cannot take 2, so this is not possible. You won't get any outcome out of here. Fine. You are fine with it. You said, I'll be choosing the other value, which is 5. I'll be choosing 5. Here you get that, okay, this is itself one possibility. And then you said that, okay, I'll be choosing 7. And you say that, okay, no possibility is there because this is already surpassed the limit. One assumption that we are considering is all are positive numbers. We don't have any negative numbers. And yeah, the sum is fixed and we have to form that sum. So can you understand what are we utilizing over here? We said that given the last number, we are taking a decision of what should be our next number. That can be 2, that can be 3, that can be 5, that can be 7. And from there we are saying, okay, this particular possibility yields us one possibility. Choosing 3 yields us 0. Choosing 5 yields us 1. And choosing 7 yields us 0. And we see we are matching it. Yeah, it is matching over here. So this is basically what we should be applying. Make sense? So this is also going to be an exponential approach, and we can understand there are so many possibilities. But again, backtracking has been designed to make things easy, make things look easy. So in backtracking, what we say is we have got sum up to here, and my parent is telling me that my parent has considered up to some number, maybe up to 3. Okay. Now I will say I can take 3 or any particular number, and I'll instruct my child that you will take only numbers from here. You cannot take before this. So I can say, okay, one possibility is I'll be choosing 5, and I'll tell my child you can choose to take numbers from 5 or 6. Basically, from 5 or after this. Make sense? So this is basically going to be the approach, and let us see how easily we can code it. So we can say I'm copying this, find subsets. I'll be copying this onto what was the combination sum? Yeah, combination sum dot cpp. If you have any questions, you can ask. So now I'll be changing this compute something like this, and let us maybe, okay, we can keep this. Instead of subset, I'll choose way. Maybe this is one way of doing it. Okay, now way is empty, and we will pass this way. Okay, and I will say that your first number, okay, a we have, and the first number is going to be 0. There is, or we can say index is going to be 0, the first index, and the rest of the things will be almost the same. We will call the function compute, and let us see what we'll be doing. Inside this function compute, we will say that instead of this, we'll have something like this. If car, or if we say that the sum of the subset, which is initially 0, we are passing the sum now. Okay, ll sum. So if we find that the sum is equal to the targeted sum, so let us take that as input, cin target. So we are going to have something like target as well, and we are going to take that as input, target. Now we'll be passing this ll target. Okay, and we can say that if it matches, if sum is equal to target, we'll basically add this. We'll basically add this possibility, right? Or we can say something. Okay, yeah. Over here only we can do this. Yeah, we can add it to the subset in this manner. List dot pushback subset. And the other cases are something like this. Now I've understood that, okay, I'm not going to have it equal to target. So if my sum is exceeding the target, then it is meaningless to proceed from here. I can just say return. Right? I can just say forget it, because you have already crossed the target. Now I'll say that, okay, this is your current position. So from the current position, try to explore what elements you can add to the current subset. So this is what we'll be doing. LLI equals current I less than n I plus plus. These are the number of ways in which you can choose the next element. What can you say now? Subset dot pb a of I, right? And on adding this, you will see, now compute the rest of the thing for me. And how will it go? Current current will still be the last one. So over here, this car actually means what is the last value that was passed to us, or what is the last value that has been taken, or which value we can start from. This is what our parent has instructed us. So we will tell its child that you can take again from last, since repetition is allowed. You can take from last, but you cannot take from before. Or basically, if you choose the ith number, if you choose ai, basically you allow your child to start from I. You say your child can start from I, and then you say you can choose this subset, and you can have this list, and you can have pretty much the same things. A sum plus, what is the sum currently? It's sum plus ai, and then you say target. And again, conservation of mass or values, whatever you say. When your task is done, you will say now remove it. Subset dot popback ai, or sorry, popback, right? And this should be able to form it. Let us see what this helps in forming. G++ combination sum. Okay, auto. Okay, G++ combination sum. Now let us choose this particular example only. 2 3 5 6 9 2 3 5 6. So we will have 4 numbers, and those 4 numbers will be, dot slash a dot out. 4 numbers will have 2 3 5 6, and the sum will be equal to 9. So we can see 2 2 2 3, then 2 2 5, then 3 3 3, then 3 6. This is how it is forming. So observe this and let me know if you have any doubt at any point. So first we decided that our first number will be 2, and we told our child that you can choose again from the same index. So it chose 2, and then again its child chose 2, and then we saw that this particular possibility was coming. Then all the other possibilities got ruled out, and we are having 2 2 5, 3 3 3, 3 6. Does it make sense? So see how easy the code looks. You are doing so many things, but see how easy the code looks. At every point of time you are saying that if the sum is equal to target. Why is this being printed only once? Because after adding an element you are calling this compute. So if after adding this element you are reaching a possibility, then it will automatically print this. Okay, why isn't it printing different permutations? Because we are fixing this particular order. It will go from last to n. So over here, if it decides that I'll be choosing I which is greater than last, it cannot come back to I minus 1 or I minus 2, because you're always fixing it that okay, start from I only. So after this, last becomes this value I. So it will always say that now I will be equal to last or greater than this. Okay, and in this way all the children will actually abide by its parent. Does it make sense? So if we dry run this, how is this occurring? We'll have something like this. This particular example, let us see how the dry run occurs. We'll have something like this. First the guy will choose. So these are the various tests. First the guy chooses 2. It says his child you can choose from 2. So it chooses 2 2 and it makes it 4. Right? It chooses 2 2 and it makes it 4. Next the guy is going to choose, or something, let us write it. 2, it chooses 2 2. Next the guy is going to choose another 2. So you are going to get 2 2 2. Next the guy chooses, it cannot choose like, okay, it can choose another 2, so it chooses 2 2 2 2. And then what happens? Next it tries with 2, it tries with 3, it tries with 5, it tries with 6. Whatever it adds to this, it will see that it will cross the limit. It will see that the first time it adds something like this, 2 2 2 2 2. It has crossed the limit, right? Then you will see that it will try with 2 2 2 2 3, and this will also cross the limit. You can actually print it over here. You can actually try printing over here. If sum equals to target, you can like print all these possibilities. Let us see what these possibilities are. You will get something very similar to what we saw over there. I think vector cannot be printed. I will try this, but maybe it cannot be printed directly. It will say something like overloading of that operator. Yeah, it's so long an error. So we can say that for LLX in subset, we'll be printing everything in X. So cout X, something like this, and then we'll be printing cout endl. So you'll actually see that 5 2s is going to come over here. 2 2 2 2 2. That is first going to come. Let us check that. So I have 4 numbers 2 3 5 7, and then I'm going to have, or 2 3 5 6, I think we had 4 numbers 2 3 5 6, and then we are going to have the sum as 9. So you can see the first, before everything, you are going to get all the bad possibilities. You are going to get 5 2s, just the way we showed. We are going to get 5 2s, and then we are going to get 4 2s and 1 3. So you can see 4 2s and 1 3. These are going to be reduced. Then 4 2 and 1 5. All these, using 4 2s, it is going to check all these possibilities. Then it understands that using 4 2s it is not possible to find anything. Then it uses 3 2s and it tries all these things. Using 3 2s, after adding 1 3, it is going to get this particular possibility. 2 2 2 3, this one. And then it will try even more. Right? It will try even more and it will face all these possibilities. Now you can say, when I had chosen 2223, why am I getting this? When I had chosen 2223, I automatically know that I am reaching the target sum. After this, why am I adding this 3? Why am I adding this 5? Right? Can you understand what is the question? Using 2223, you are already getting the sum. And why are you choosing 3? Why are you choosing 5? Why are you choosing all these things? Can anybody answer? Why are we getting all these things? The idea basically is we are doing some unnecessary computation because after this part we are not preventing it from executing all these things. It is executing all these things, so we should actually prevent it. After it is pushing it, what happens is it comes over here and again tries pushing other things. See, this is sum equal to target. We should have stopped. The moment it becomes sum equal to target, we can say that okay, now return. Your job is done. Now we will see that okay, now those possibilities are not going to come. If we have 4, 2, 3, 6, I think we have 2, 3, 5, 6. Okay, over here, what have I kept? 2, 3, 5, 6. Okay, 5, 6, and we are having 9. So now you can see those possibilities will not come. 2, 2, 3, 3 now no longer comes. Sorry, 2, 2, 2, 3, 3. That problem that now nowhere comes. 2, 2, 2, 3, 3 is never going to come because it returns right from here. But all the answers you'll be getting over here. You ignore this part. You can see all the answers you'll be getting in this part. 1, 3, 5, 6. Is this the, no, it is 2, 3, 5, 6. Okay. 2, 3, 5, 6, and we have 9. So you can see all the 4 possibilities are going to come. The number of computations will only be lesser. Makes sense? Okay. Now think about another problem. This is also a very this is one of such problems which becomes very easy with backtracking, but without backtracking this is not that easy. The problem is palindrome partitioning. So whenever we have some palindrome AAB, whenever we have some string, there are some ways to partition this into palindrome. You can have something like this. You can have A, you can have A, and you can have B. So all the 3 are palindromes, right? Then you can again, palindrome means the reverse thing is the same as the current string. Then you can say that okay, if we take the first 2 characters together, we are going to get another possibility. Makes sense? So these are the 2 ways we can have the palindromes. We can partition it into palindromes in these 2 ways. So in order to find this out for any string, what can we do? For any given string, we want to find a number of ways in which we can attach palindromes and form this. How can we, like the length of the string will be small enough, it will be less than or equal to 16 once again, or less than or equal to 20. Find out how many ways, or basically what are the ways. You have to print each of these things. How can you do that? So while you think on the problem, it always makes sense to know about who is teaching you, who is talking all these things, which some of which make sense, some of which does not make sense. I am Saptarshi Mukharjee, and I have been an educator at Unacademy over the past few months. I have graduated from IIT Bhilai, having pursued BTech from there, or BTech honors, BTech with the specialization in computer science and engineering. Uh, I have been a master at Code Forces, and I have been a 6-star rated Code Code Chef, and I have been to the ICM ICPC regionals in 2019. Apart from this, I'm going to join Google soon, so that is what my full-time role is going to be, full-time software engineer at Google. So that's pretty much about myself. You can find me on Unacademy. You can see my videos on Unacademy. Every day I'm taking some videos. Sometimes they are shifted to YouTube. Then I'm able to take it over here. and you can use my referral code Saptarshi1729 in order to see all those videos for free. So all the videos won't be according to your taste. Some will be harder, some will be easier. I take all possible kind of videos. Using this code, you can actually see all the videos for free. Whatever are available as special classes, you can see them. Okay. This is the same as my code forces profile as well. So think about how you can solve the problem. We won't be coding it totally. We'll just be discussing it. Till then, I think I'm supposed to cover something for Unacademy too. Yeah, there you go. So these are the 4 batches that are being offered currently on Unacademy. You have Transpire, Eklavya, Brahmastra, Mahayodha. Transpire and all of them have started either on 20th or 21st July. They all have got a structured learning path and one subscription and unlimited access to all batches or courses. You have the best coders of India's educators, and yeah. In Transpire, you have OS, DBMS, networking, all these things, which you might have covered in colleges. You have networking, RDBMS, operating systems, object-oriented programming. In Eklavya, you are basically transformed from a beginner to an advanced coder. You cover first the beginner concepts, then the intermediate concepts, then the advanced concepts. So it might help you like follow a structure and learn the things. And you can see these topics are quite advanced. Then you have the Brahmastra, which is only for interview related preparation. So we cover only the interview related topics in this batch. Okay. You have the final 2 weeks only on interview problem solving. Then there is Mahayodha, which I am taking currently. This is on advanced programming. This launched on 20th July. On 20th July, actually the second part started. So I have taken advanced combinatorics and those things first, then advanced dynamic programming, then segment trees, then advanced concepts of graph theory, mixed problem solving. This is the old list of educators. There's some of your educators. You have live interactive classes, practice relevant problems, doubt support. These are again some of the profiles. You can have a look at them. And this is the subscription plan. 1 month 6,000, 3 months 16,000, 12 months 33,000 only. So you can see from 6 months to 12 months, actually the price difference is less because the discount is high. So you can think about this. You will get 10% off on the referral code. On top of this, if you use my referral code Saptarshi1729, you'll get caps lock, small letters, anything, whatever you use. Okay. For the special classes as well as for your plus classes, you will get this. Okay. That closes it, I think. Yeah. So how can we solve this problem? So I'll be finishing it soon because now we basically I have another class from 7 p.m. So you can solve this. The important thing is when we see that we have got a palindrome over here, when we see that we have got a palindrome up to a certain position, say I minus 1, now I can focus that our next palindrome has to start at I. So I can check for all possible j from I plus 1 to n minus 1, all possible j I can try. What are the palindromes that I can form from I to j? And whenever I see I can form a palindrome, I can say that okay, now call a subset, call another function and check what we can form from j plus 1 to n minus 1. I'll be searching for that. So you can understand that whenever I started the search for this one, that from the I what I can have, I've reduced it to a problem saying that now I'll be searching from j plus 1. J will belong, j is the last character that I'll be choosing for my palindrome. So I can say from here that suppose I'm starting it, I started my journey, so my first palindrome will be either A or AA or AAB. I know AAB is not a palindrome, so I'll not take it. These two are palindromes, so I'll call for it. That okay, I've chosen the first one as the first palindrome. Now form palindromes using this part. Using this part, there is only one palindrome or palindromic sequence possible, A and B. This is one palindrome, this is one palindrome, this is one palindrome. Using A, you know that there is again one palindrome possible, which is B itself. Okay. You will also try with AB, but you will not find any prospect. So this is the way we can do this. This is the way we can generate the palindromes. Does it make sense? Do you want me to code it? This will again be like very easy to code. Directly you can code and you can understand how it is working. So I hope you won't be requiring the code. You can let me know if you want me to code it. I'll wait for 1 or 2 minutes before closing. Should I code it? Yes or no? Another 40 seconds. Should I code it? Okay, then I hope you'll be able to code it and appreciate its implementation. So that's it. We have covered an important topic for interviews today. And what else? Yeah, let us know through your comments or whatever that what future videos you might be looking for or on what we should be making future videos. We can try on them. Okay. Take care and bye. Have a nice evening.